And welcome to our video on the complex exponential. First, remember that if z is a complex number, then we define e to the z to be the power series sum k equals 0 to infinity of z to the k divided by k factorial. This is the same power series definition as for the real exponential, except now we're using the letter z instead of x. We've worked with the complex exponential throughout the course, most especially with differential equations and Fourier series and transforms, but there we typically had something like e to the I times x, where x is real, and now we're going to go whole hog into allowing z to be purely complex, any complex number. And we will develop a number of properties of this map of z into e to the z, many of which are rather different from what we know about the real exponential. We will also sometimes write this as exp of z, especially when the stuff that we're putting in the exponential is just too big to fit comfortably in the typesetting. So first, you prove convergence of this series just as you do when z is real. You use the ratio test. Second, we remember Euler's formula. If x is a real number, then e to the ix equals cosine of x plus I times sine of x. We've used this tacitly throughout the course, but now is a good opportunity to look through the proof of how you get this identity from the series definition. So e to the ix is the sum from k equals 0 to infinity of the product ix raised to the power k over k factorial, which is the sum from k equals 0 to infinity of I to the k times x to the k over k factorial. Now consider what I to the k can be. If k is an even number, so you have 2k there, then I to the 2k is going to be I squared raised to the power k, which will be minus 1 to the k. And so I to the 2k plus 1, when the power is odd, is going to be I to the 2k times I, which will be minus 1 to the k times I. So now let's split our series for e to the ix into a sum of even terms and a sum of odd terms. So we have the sum from k equals 0 to infinity of I to the k times x to the k over k factorial is the sum over the evens plus the sum over the odds. So the sum over the evens is I to the 2k times x to the 2k over 2k factorial, plus the sum from k equals 0 to infinity of I to the 2k plus 1 times x to the 2k plus 1 over 2k plus 1 factorial. And let's just replace those I to the 2k's and I to the 2k plus 1's with what we calculated above. So now we have a series that is sum k equals 0 to infinity minus 1 to the k x to the 2k over 2k factorial, and another series I times the sum from k equals 0 to infinity of minus 1 to the k x to the 2k plus 1 over 2k plus 1 factorial. Now this may not seem to be any better, but depending on our calculus memories, we might recognize these as power series for two familiar functions of a real variable. Namely, cosine of x is the sum from k equals 0 to infinity of minus 1 to the k times x to the 2k over 2k factorial, and sine of x is the sum from k equals 0 to infinity of minus 1 to the k x to the 2k plus 1 over 2k plus 1 factorial. This is how I personally like to define sine and cosine as power series. So if you accept these as the definition of sine and cosine, then you get e to the ix is the first series plus I times the second, which is cosine of x plus I sine of x. This also gives us a new polar representation formula. Remember, we said in polar coordinates that any complex number has the form z equals modulus of z times the sum cosine of principal argument of z plus I times sine of principal argument of z. Of course, you could replace the principal argument with any other value of the argument that you like. But now, from Euler's formula, this just says that z equals modulus of z times e to the I principal argument of z, or e to the I times any other argument of z. And so we will use this representation quite often, this combination polar and Euler's formula. We retain a very familiar and useful property, the sort of additivity, multiplicativity of the complex exponential. If you have two complex numbers z and w, then e to the z plus w is the product e to the z times e to the w. And you prove that using the series definition of e to the z plus w, the so-called binomial theorem, and the so-called Cauchy product formula, which we'll meet at the end of the course when dealing with series solutions of differential equations. Take my word for it, just trust that e to the z plus w is e to the z times e to the w for all complex numbers z and w.